Hi everyone, and welcome to this series of practice problems about different topics in numerical method. And this is set number 4, where we'll be actually solving questions about solving nonlinear equations. The difference between this set of notes and the previous one, here we'll be solving multiple equations with multiple unknowns. In the previous set, we will try to find the roots of a single nonlinear equation. So let's start. So this is the first equation using Gauss-Seidel method. We want to solve this 2 by 2 system. And here we are giving two initial conditions. The first one is x1 and x2 both equal to 1. Here x1 equal to 1 and x2 equal to 2. And you are asked to continue the iterations until the error, the approximate relative error, is less than 0.001. So the first thing that we need to do is to put the equations in the form of x1 equal to g1, x1, x2, and x2 equal to g2, x1, and x2. So from the first equation, take x1 as a common factor. So we have 1 plus x2 equal to 10. From this, your x1 is equal to 10 divided by 1 plus x2. For the second equation, your x2 is equal to 6 minus x1. So this is setting up the equations. Let's start the iteration. So let's start x1, the first iteration, is equal to 10 divided by 1 plus x2, the initial iteration, which is 1, and this will give me 5. x2, the first iteration, is equal to basically 6 minus x1. Now x1, I have two values, the initial guess and 5. I use the most updated one, which is 5, and this will give me 1. Then go for x2, 1 is equal to 10 divided by 1 plus x2, the first iteration, which is 1 again. So we are having 5, and this is x1, sorry, and here x2, the second iteration, is equal to, again, 6 minus 5, which is equal to 1. So obviously the error is 0, and we already converged. This is unlikely to happen, but in this specific example, with these equations, we converge to 5 and 1. When we see and test the system here, substitute x1 equal to 5 plus 5 times 1. This is indeed equal to 10. And 5 plus 1, this is equal to 6. So that is the solution. Now, we want to see what will happen if I change the initial conditions. When you change the initial conditions, now we want to find x1 of the first iteration, which is equal to 10 divided by 1 plus x2, the initial condition, which is 10 divided by 1 plus x2 was 2. So this is equal to 10 divided by 3, which is equal to 3.3333. I will have, you can have only 4 significant digits. Now, x2, the first iteration, is equal to 6 minus x1. Now we will use this iteration, which is 1, the first iteration. And this will give me basically 6 minus 3.333, which is equal to 2.6667. Okay. Now let's move to the second iteration. When we move to the second iteration, you will find that this is the value of the second iteration, that x1 of the second iteration equal to 10 divided by 1 plus the most updated value of x2. So we get 2.7272, and x2, second iteration, will get 6 minus the most updated value of x1. So we get 3.2727. Obviously, the difference here between these two is much larger than 0.001, and we keep doing this, and we find that we only reach to the required accuracy at the 10th iterations, And you can see here that x1 looks converging to 2 and x2 converging to 4. And basically, when we substitute the equations, which are x1 plus x1, x2, so this is will equal to 2 plus 2 times 4, which indeed is equal to 10, the output of the equation. And the second one, x1 plus x2 equal to 2 plus 4, which is equal to 6. So this is another solution. But you see here, the initial guess, just by changing x2, we went to totally a different answer. And while in the first answer we converged in the first iteration, this one it took us 10 iterations to reach to an answer with the required accuracy. So that tells you that the initial guess is extremely important, especially when you have multiple answers for your equation. Now let's go now for the second equation. And the second question, basically here, we will be working on Newton-Raphson method. We want to find the solution for these two equations. And we will start x1 equal to 2, x2 is equal to 3. So that is my vector. Okay, my initial guess is equal to 2 and 3. So that is my initial vector for the solution. And we'll use only two iterations. Okay, so as we know it, that x at iteration I plus 1 is equal to, as here, a vector equal to x I, the iteration before that, minus, then we will have here your f prime of x I matrix inverse times f of x of I. So that is the general formula for the Newton-Raphson method. Okay, so I know this. I need to find f prime and f. So let's start with f of x is equal to x1 square minus 2x1 minus x2 and x1 square plus x, this is minus 3 because it has to be equal to 0, plus x2 square minus 41. So this is your f of x. Then we want to substitute f of x at the initial guess. And this will give me a value of minus 6 minus 28. Then let's find f prime of x. So we'll take the derivative of this. So basically here we have 2. This is your g1 of x, and this is your g2 of x, or f1 of x, doesn't matter what you call it. So this is the partial derivative of g1 with respect to x1, the partial derivative of g1 with respect to x2, the partial derivative of g2 with respect to x1, the partial derivative of g2 with respect to x2. So this is how the matrix should look like. So here we will take the partial derivative of this with respect to x1. So we will have 2x1 minus 2. The partial derivative of this with respect to x2 is minus 1. The partial derivative of this with respect to x1 is 2x1. The partial derivative of the second function with respect to x2, which is 2x2. So that is your matrix. Now we substitute x equal to 2, x1, and x2 is equal to 3. So your f of x, initial guess, will equal to basically your 2 minus 1, 4, and 6. So from this, you want to find now the updated value of your x. The most updated value will equal to x0, which is 2 and 3, minus the inverse of this, 2 minus 1, 4, and 6, inverse, times the value of the function, which is minus 6 minus 28. Now, when you do this, you solve for this, you will find your x of 1 will equal to 6 and 5. So this is your basically your second, or this is your first iteration. So this is the initial iteration, and this is the first iteration. And as you know, this is a 2 by 2 matrix. So how to find, so if this is like A, B, C, D, what is the inverse is 1 over the determinant. You just replace D with A and A with D, just interchange them, so this becomes D and A, and change the sign of B and C components, and the determinant is nothing but AD minus BC. So this is for your information if you forgot how to find the inverse of a 2 by 2 matrix. Now we repeat exactly the same thing for the second iteration. So here I have the answer for you. So this is your now x of the previous iterations. This is the functions. Now I substitute now the values. This is your x1 and this is your x2. So substitute the value, you get this vector. This is the inverse of your x. The derivative of the x with respect to x1 and x2. Substitute the values of 6 and 5. So you get this. And then this is your x. Now the second iteration equal to x1, the previous iteration, which is this vector, times these values that we already calculated. And then you can find x2 is equal to this vector, the matrix inverse times 16, 20. And then when you substitute the value, this is your second iteration. And we stop here because we asked for only 2 iterations. The third question is also about Newton-Raphson method. And here, because it's a 3 by 3 system, it says here, use Gauss elimination to solve the system of equations. And this is the starting point, 1, 1, 1. So we will do only 1 iteration here. Okay, so your f of x, y, and z is equal to x cubed minus 10x plus y minus z plus 3, y cubed plus 10y minus 2x minus 2z minus 5, and finally x plus y minus 10z plus 2 sine of z plus 5. Then we will find the partial derivative. So we want to find f prime or f derivative of x, y, z, the Jacobian matrix, which is basically the partial derivative of respect of the first function, f1 with respect to x, partial derivative of f1 with respect to y, the partial derivative of f1 with respect to z, and then so on and so forth for the other components. So let's do that. The partial derivative of this with respect to x is 3x squared minus 10. The partial derivative of this function with respect to y is 1, and for z is minus 1. And then the partial derivative of the second function with respect to x is just minus 2. With respect to y is 3y squared plus 10. With respect to z is minus 2. Finally, the third function with respect to x is 1, with respect to y is 1, with respect to z minus 10 plus 2 cosine of z. Now, you need to substitute the values, okay? And when you substitute which values, so this is 1, 1, 1, you have to pay attention that for the cosine function, you have to use radian. Make sure that it is in radian. So when you substitute, you will have this is minus 7, 1, minus 1. So this is your Jacobian matrix. And then minus 2, 13, and minus 2. Finally, 1, 1, and minus 8.9194. the question says here use 5 significant digits. And this is what we did. So now we will come and try to find our x1, the first iteration, which is equal to x0, which is 1, 1, 1, minus 7, 1, minus 1, and minus 2, 13, minus 2, and 1, 1, and minus 8.9194 inverse times minus 6, 2, minus 1.3170. Now, what is this? Basically, this is when we substitute the value here of 1, 1, 1, we will get minus 6 to minus 1.3170. Now, because this is a 3 by 3 system, we want to solve for this. Then we put it in the format of AX equal to B. So the system of equation will be like this: minus 7, 1, minus 1, minus 2, 13, and minus 2, 1, 1, minus 8.9194. Put it in the terms of the augmented matrix, minus 6 to minus 1.3170. So we want to solve this because at the end of the day, this will give me a vector. So we can basically put it in the augmented matrix, use Gaussian elimination, and solve for that instead of having or going through the hassle of finding the inverse of a 3 by 3 matrix. So that is also good of revising for us basically the Gauss elimination. So the first row, as we remember, doesn't change. So this is minus 7, 1, minus 1, and this is minus 6. Now the second row will be R2 minus 2 over minus 7 times R1, and this will give me 0, 12.714 minus 1.743, and this will give me 3.713. Then we'll go for the second row, same thing here. It is R3 minus or 1 over minus 7 times R1, and this will give me 0, 1.1429, and minus 9.0623. Please, it's good that you do go through this exercise and make sure that the numbers are correct. Minus 2.1741. Okay, so now we make all this 0, and before that even we checked here, this is the highest number, so we don't need to do any pivoting. Same thing here. Now when you look here to the second row, this is the highest, this is higher than the third row, so I don't need to do anything here. So now I want to make this equal to 0. So now we would go for R3 minus 1.41429 divided by 12.714 times R2. And doing this, we will get this matrix: minus 7, 1, minus 1, minus 6. This doesn't change. 12.714 minus 1.714, 3.7143. And then you will have 0, 0, and minus 8.9082, and here minus 2.508. Now we have it in the last format. Now we'll do back substitution. We'll start with x3, which is equal to minus 5.508 divided by, because here we just divide this with this, so this is not 5, this is minus 2.508 divide minus 8.9082 and this will give me 0.28154. Make sure you have 5 significant digits. Your x2 when you substitute equal to 0.33010, and x1 will equal to 0.86408. So we found all the vectors. So from this, your x now, first iteration will equal to 111 minus, now we take them this order, so this is 0.86408 x1, 0.3301 x2, and 0.28154 x3. Do this, this is will give me 0.13592, 0.6699, and this will give me 0.71846, and that is the solution using one iterations and combining the Newton-Raphson with basically the Gauss elimination.